Last time, we took a real lithium cell apart, a gray graphite anode on one side, an ochre metal oxide cathode on the other, and between them, a cyan sea of electrolyte carrying lithium back and forth. We watch those ions move, one way when the cell charges, the other way when it drains. But we never answered the question hiding underneath it. Nothing pushed them. There was no pump in there, no fan, no tiny hand shoving ions along. So why do they move at all? Tonight, the answer, it's one number you already know by name, voltage. And once you see where voltage truly comes from, you'll be able to read the single most important graph in all of battery science. To crack this, let's start with something you already trust completely. A ball on a hill rolls down, never up. Water runs downstream, not back up the mountain. Heat always flows from the hot thing to the cold thing. Look closely, and it's the same story every single time. A system sitting at higher energy slides toward lower energy, and it hands over the difference along the way. That's the one rule nature never breaks. And here's the promise for tonight. Lithium inside a battery obeys that exact same rule. It moves because moving lets it drop to lower energy. The only trick about the thing we have to learn to see, is where the hill actually is. So where is lithium's hill? Here's the key idea, and it's simpler than it sounds. A lithium atom is not equally comfortable everywhere. Tucked between the carbon layers of charged graphite, our gray anode, it sits loosely, reluctantly, at high energy. That is the top of the hill. But inside the ochre metal oxide cathode, lithium bonds tightly. The oxide genuinely wants it there and holds it at low energy. That is the bottom of the hill. Same atom, two very different energies depending only on which host it's sitting in. So picture two shelves, a high gray shelf for lithium and graphite, a low ochre shelf for lithium and the oxide, and lithium, like the ball, like the water, like everything else, would simply rather be low. Now we can finally name the answer to our mystery. Moving one lithium from the high gray shelf down to the low ochre shelf releases energy. That release is exactly the size of the drop. But to turn released energy into a voltage, we don't want the raw energy. We want the energy per unit of charge that moves with it. Energy divided by charge. That is the definition of voltage. Written cleanly, the open circuit voltage equals minus delta G over N times F. Delta G is the energy released as the reaction runs forward. It's negative because energy comes out. N is the number of electrons riding along with each lithium, and for lithium, that is simply 1. And F is Faraday's constant 96,485 coulombs per mole, the charge carried by one whole mole of those electrons. Read it plainly. The energy lithium gives up, divided by the charge that carries it, is the voltage. That's the heart of this entire episode. There's one word in that name we have to take seriously. Open circuit. It means there is no wire connecting the two electrodes, and the circuit is open, the switch is off, so no current can flow at all. The ammeter reads a flat 0. The cell just sits there, perfectly balanced, at rest. And that is exactly when the voltage is honest. With nothing flowing, there's no friction, no losses, nothing muddying the reading. The voltage you measure across the terminals is purely that energy drop we just defined in the cell's true thermodynamic voltage. We call it the open circuit voltage, OCV for short. Hold on to this. For most of tonight, every voltage we talk about is this calm, resting number. The messy question, what happens once current actually flows, we're saving for the very end. But here's the move that makes everything click. That rested voltage is not actually one fixed number. As you discharge the cell, lithium steadily leaves the graphite and fills the cathode. So how full the cell is keeps changing. And we call that the state of charge, 100% when full, 0 when empty. And here's the subtle part. As graphite fills, its gaps get crowded, and squeezing in one more lithium costs a little more. As the cathode fills, its appetite for lithium fades. So the height of each shelf shifts, the drop shifts, and the rested voltage shifts with it, which means at every state of charge, the cell has its own open circuit voltage. So let's plot one against the other. Voltage up the side, state of charge along the bottom, and let the cell sweep from full on the right to empty on the left. If the voltage slides, then there must be a curve. Let's go build it from a real cell. Here's a real lithium-ion battery, fully charged. Let's run it down slowly and watch what happens inside. On the left is the graphite, packed with lithium right now. Every glowing dot. On the right, the cathode, waiting to receive it. We start using it. Lithium leaves the graphite, drifts through the liquid in the middle, and fills the cathode on the right. Now keep your eye on the voltage. For a long stretch, it barely moves. The graphite empties one neat layer at a time, so each lithium costs about the same energy. This gentle, flat part is called the plateau. Past the middle, the curve tips downward as the structure rearranges. And near the end, the last lithium holds on the hardest, so the voltage drops off a cliff. Plateau, slope, cliff, that whole shape is the OCV curve. And you just watch the cell draw it, point by point. Before we read the shape of that curve, let's pause inside the cell for a moment, because every feature we're about to read lives right in here. On the left, the negative electrode. Graphite, about 85 microns thick, built from gray particles just under 6 microns across. On the right, the positive electrode, the layered metal oxide around 76 microns, in ochre with slightly smaller particles. A thin separator, just 12 microns, splits them down the middle. And filling every gap, the electrolyte, a 1 molar lithium salt solution, our cyan field, through which the lithium ions actually swim from one side to the other. This is not a cartoon. The particle size, the layer thicknesses, the concentrations, they're the real numbers for this exact cell. Keep this picture in your head because the bumps and plateaus in that gold curve are these particles changing, one ordered phase at a time. Now we can read the curve, and we start with those long, almost flat stretches. They are the fingerprint of the gray graphite anode, and they come from something genuinely elegant called staging. Lithium does not pile into graphite at random. To stay out of each other's way, the atoms fill the galleries between the carbon sheets in an ordered pattern. First every second gallery, then every gallery. Across the broad middle of the curve, lithium settles into an ordered arrangement chemists write as lithium carbon 12, with lithium in every second layer. Toward full, it packs tighter into lithium carbon 6, every layer occupied, as full as graphite gets. And here is the single most important sentence of the whole episode. A flat plateau is where two of these ordered phases coexist, and the cell is converting one into the other. While both phases sit side by side, the energy per lithium is pinned, so the voltage barely moves, even as a huge amount of charge flows. A plateau is not the cell being lazy. It is the most happening, a phase transition hiding behind a flat line. Now the parts between and beyond those shelves. Wherever the curve clearly slopes, the graphite is sitting in a single phase whose composition is changing smoothly, so the energy per lithium and the voltage slides steadily as it fills. Say it as a pair. A plateau means two phases coexisting and the voltage pinned. A slope means one phase changing and the voltage moving. And then, at the far left, near empty, the most dramatic feature of all, the cliff. The very last lithium is the hardest to pull out of the graphite. As the anode runs dry, its potential swings violently upward, and since the cell voltage is the cathode minus the anode, that climbing anode drags the whole cell voltage down fast. The curve dives from about 3.4 volts to the 2.5 volt cutoff over just a thin sliver of charge. This is exactly why your phone can sit at 10% and then drop to 0 in what feels like no time. The curve was warning you the whole way down. You just couldn't see it clearly because under load the voltage is bent. Which raises the obvious question, where do those slopes come from exactly? So let's pin down where those slopes actually come from with one more equation. For a single electrode, the potential follows the Nernst equation, a standard value U0 minus RT over NF times the natural log of how full the host is. Don't let the symbols scare you, see? The shape of the idea is the whole point. Inside a single phase as the host fills, That logarithm changes smoothly, so the potential slides, and there is your slope. But inside a two-phase plateau, the balance between the phases is fixed. The logarithm is frozen, and the potential stays flat. There is your plateau. One equation both features, and it even sets the scale of the gentle steps. At room temperature, RT over F works out to about 25.7 millivolts. That tiny number is the natural size of the soft voltage wiggles you see all along the curve. So Nernst is the rule behind the shape, and now we can finally take the whole curve apart into the two electrodes that built it. Now the reveal that ties the whole curve together, and it corrects the single most common mistake people make. There is no such thing as the voltage of one electrode on its own. Voltage is always a difference. So let's split the gold curve into the two pieces it was built from. Up top, in ochre, the cathode's own potential, measured against lithium metal. It rides high between about 3.5 and 4.2 volts, sloping gently as it fills. Down at the bottom in gray, the anode's potential, low near 1/10 of a volt, carrying those little staging shelves we just read, and climbing at the very end. Both are measured against the very same reference, lithium metal defined as 0 volts. Now subtract the gray from the ochre at every single state of charge, and the curve you build is the full cell voltage, exactly the gold OCV curve we've been reading all along. So the cell voltage equals the cathode potential minus the anode potential. Every plateau, every slope, even that cliff, they were just these two landscapes combined. There's one honest question left. How do you actually measure such a calm, rested curve on a real working cell? You can't just discharge it quickly and read the voltage as you go, because, as we'll see in a moment, the very act of pulling current bends the reading. So instead you tiptoe. The method is called GITT, galvanostatic intermittent titration. The idea is patient and clever. Send a small, brief pulse of current to move a tiny known slice of lithium, one small step of charge. Then stop and wait, often for hours, while the lithium settles and the voltage relaxes all the way back to its true resting value. Record that one rested point, then pulse again, rest again, record again, marching step by patient step across the whole state of charge range. Each dot you place is one true equilibrium point. Join the dots, and you've traced the real open circuit curve, the gold line, with none of the sag that current would add. Now notice why this has to be so slow and why it matters so much. The OCV curve is, by its very definition, the resting landscape, the cell with no current and no losses. The only honest way to see it is to let the cell come to rest at every step. Rush the measurement, and you're no longer reading the landscape. You're reading a voltage already bent by the act of flowing. And that brings us at last to the one question we've been circling all episode. The instant you actually use the battery, current flows. So here is the rested gold curve. Now connect a real load and pull current, a 1C discharge, and the working voltage drops below the gold curve right away. Pull harder, a 2C discharge, and it sags even further. That distance between the resting voltage and the actual working voltage has a name, overpotential. Everything tonight was about where lithium wants to go and how much energy it releases getting there. Overpotential is about the road conditions on the way, and that is exactly the story we open next time. So, why do the ions move? Now you can answer it yourself. Lithium sits at high energy in charged graphite and at low energy in the oxide, and it moves simply because moving lets it drop. That drop, divided by the charge that carries it, is the voltage. Sweep it across state of charge, and you get the OCV curve, the most important graph in the field. We even watched a real cell draw it, with its plateaus from graphite staging, its slopes from single phases changing, and its cliff where the last lithium clings on. And the whole curve is just the cathode's potential minus the anode's, measured at rest. But notice what we never asked tonight. Not where lithium wants to go, but how fast it can get there, and why the voltage sags the very instant you actually use the cell. That sag is called overpotential, and unpacking it is the whole of episode 3. Kinetics, why the ions are slow, why cells warm up, and why fast charging fights physics. I'm Faraday. Keep exploring.